In this video, I am going to explain the working operation of Clapp's oscillator and its derivational steps to find frequency of oscillation as well as gain requirement. So this is the basic amplifier, common emitter amplifier. R1, R2 provides the DC biasing, and RE is connected between emitter and ground, and it is bypassed using CE. So RC is the load resistance. So this is the output terminal. The output terminal, the input terminal, both are kept open to connect the feedback network. As we know, any oscillator circuit contains two elements. One is amplifier circuit, second is feedback network. So this entire circuit is nothing but basic amplifier circuit. Now we are going to connect the feedback network between input and output. So now I am connecting here. Now we formed the entire oscillator circuit. So here Colpitts and Clapp, both oscillators are common in structure. Only small modification is made is, so in the Z3 reactance, we are going to connect two components, the series combination of L and C3. In Colpitts, we have only inductor in this area, but we are going to add one more capacitor, which is series combination with the inductor. Due to this, what happen is reactances will be changed first. So Z1, Z2 is general, that means 1 by j omega C1, and Z2 is 1 by j omega C2. But Z3 is differ comparing to the Colpitts oscillator by including the 1 by j omega C3 here. So Z3 becomes as j omega CL plus 1 by j omega C3. And as usual, we have to take the general equation of LC oscillator. Here it is the general equation of LC oscillator, Hie into Z1 plus Z2 plus Z3 plus Z1 Z2 into 1 plus Hfe plus Z1 Z3 is equal to 0. So let it be equation 1. In this equation, we are going to substitute Z1 as 1 by j omega C1, Z2 as 1 by j omega C2, and Z3 as combination of 1 j omega L plus 1 by j omega C3 in the equation. When we substituting, we get Hie into 1 by j omega C1 plus 1 by j omega C2 plus j omega L plus 1 by j omega C3 plus the second term 1 by j omega C1 into 1 by j omega C2 1 plus Hfe plus 1 by j omega C1 into the third term j omega L plus 1 by j omega C3 is equal to 0. Now we separate the entire term as imaginary part and real part. Okay. So here this j gets multiplied, hence it becomes as minus. Here also, here we have the j term, so taking out the j omega term, and here also we have j omega gets cancelled. Sorry, 1 by j omega C1 we have the j, here we have j omega L, here the j is in the denominator, hence we bring to the numerator, becomes this term becomes as minus. Okay, so omega L minus 1 by omega C3 we have, the j is taken out from this expression, and already we have j in the denominator, these two j gets cancelled, so this becomes as a real part. Okay, so this second term and third term becomes as a real part, whereas the first term is a imaginary part. So let it be equation number 2. Next thing, we need to find two things. One is finding the frequency of oscillation. Second, to find the condition for oscillation, that is how much Hf is required to obtain a sustained oscillation. First of all, we see how to find the frequency of oscillation. For that, we have to take the equation 2. In that equation 2, that is the imaginary part, that should be equated to 0. So this is the imaginary part. Here I keep j omega L in the left side, remaining terms to the right side all becomes as positive values, omega L square. So in the right hand side I have, in the right hand side all becomes as positive. So the j term is the common term available in all the three terms, and it's brought outside and kept in a bracket remaining terms. So here j gets cancelled in the right and left hand side. here one more term is there. Omega is common to all the three terms in the denominators. I bring out of this in the denominator and move to the left hand side, becomes as numerator. Already numerator we have omega. Now the omega becomes a square, and L is equal to 1 by L, C1 plus 1 by C2 plus 1 by C3. This equation are kept as 3. Now we need only the frequency term, hence we move the L to the right hand side, becomes as denominator. So hence we have omega square is equal to 1 by L into C equivalent. So what is C equivalent? C equivalent is nothing but 1 by C1 plus 1 by C2 plus 1 by C3. Now we write the frequency of oscillation is equal to 1 by 2 pi root of L into C equivalent. The second thing we have to find is Hfe requirement. For this we have to make the real part in the equation to be equal to 0. So this is the real part. So here I have the negative term, here I have the positive term. Either one term is brought to the right hand side, becomes both the terms are positive. Okay. Now we find in the denominator we have C1 as a common value, hence I cancel C1. Similarly, here I have omega square, here I have omega. These two also gets cancelled, but here only one term is cancelled, here omega is cancelled. So I have omega here. I am going to bring to the right hand side. Already we have omega L minus 1 by omega C cube into omega. The omega brought from the left hand side is available here, as well as C2 is also brought to the right hand side as a numerator. Okay, now I multiply omega C2 inside, so I can get omega square L C2 minus this omega and this omega gets cancelled. Finally I get C2 by C3. Here I am going to substitute the value for omega square L. So that already I have kept as a equation 3. Omega square L is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So instead of, I am going to substitute here, instead of omega square L, 1 by C1 plus 1 by C2 plus 1 by C3 into C2, remaining term minus C2 by C3. Okay. In the next step, I do 1 plus Hfe is equal to multiply C2 by into the 3 terms. This becomes as C2 by C1 plus C2 by C2 plus C2 by C3 minus C2 by C3. So these two gets cancelled. I will have one value. So here these two are opposite terms, hence I cancel these both. Okay, so here I have cancelling, I have 1 here. So finally I get 1 plus Hfe is equal to C2 by C1 plus 1. So here I cancel 1. Finally I get Hfe is equal to C2 by C1. In this topic I am going to explain what is the role of C3 in Clapp oscillator. Before that, we see what is the drawback of Colpit comparing to Clapp oscillator is, here we have two capacitances. So this two series combination of these two capacitances gives a equivalent capacitance. Now what is the problem here is, the problem with this C1. So consider Z1 is the reactance of the capacitance C1, 1 by j omega C1. This reactance is parallel to the input resistance of the transistor. Now we look at the general form of LC oscillator diagram. So what happens here? The Z1 is parallel with the base to emitter resistance called the input resistance Hie. So Z1 is parallel to Hie. This gives a new resistance called Z dash. Okay, the Z dash, in this Z dash we have a transistor parameter. Usually the transistor parameter varies because of these three reasons. The Hie varies due to variations in temperature. So if the temperature varies, Hie also varies. Because of aging of the transistor, as well as the variation in power supply also causes the input resistance to change. When the input resistance is changed, automatically what happens? The equivalent impedance Z dash also changes. Okay, right. Why do we have this concern here is, Hie varies. If Hie varies, then ZL also varies, because we know that ZL is the parallel combination of Z2 and series combination of Z dash plus Z3. Now due to the temperature variation or some transistor parameter variations, Z dash will be affected, hence ZL also affected. Okay, so that is explained here. If Hi varies, then ZL also varies. When ZL varies, automatically the gain of the basic amplifier also changes, because AV is nothing but minus Hfe into ZL by Hie. Okay, so due to this capacitance, all the things are changes. If gain of the basic amplifier changes, then definitely we say frequency of oscillation also changes. From this I can give the conclusion as frequency of oscillation is not stable in Colpitt's oscillator. Hence what we do in Clapp oscillator is, in Clapp oscillator we are including one more capacitor. This is going to dominate these two capacitances. Okay, so first is neglecting the effect of C1 and C2 by introducing C3 in series with L. Okay, how this dominates we'll explain now. We have to select the C3 as very smaller comparing to C1 and C2. Hence in this expression, if I make this a small value and C1 and C2 as largest value, what happens, this will have some minimum value that can be neglected comparing to this. Finally what happens, the C equivalent becomes equal to the third capacitance value C3. Okay, right. Now from this I can say C3 dominates C1 and C2, hence the frequency is stable. Means what happens now, I can write frequency of oscillation as 1 by 2 pi root of L into CQ. Now we neglect this term, hence the CQ is nothing but C3. Okay, so purely the frequency of oscillation based on the capacitance value C3. Okay, second reason for utilizing the C3 in the Clapp oscillator is C3 used as a variable capacitor. Okay, so desired frequency can be adjusted using C3. Look at this feedback network of Clapp oscillator. Here we have to use the variable capacitor C3. Okay, so there are two benefits we get from using the capacitor C3 in Clapp oscillator. One is we are nullifying the effect of C1 and C2 by dominating the capacitance value C3. Second thing, C3 can be used as a variable capacitor, so the desired frequency can be fixed by adjusting the C3 value. Thank you.